In this video, we want to look at some of our properties of summations and how we can actually use them. So I want to take a moment or two first and talk about each of those. This is just screenshotted straight from your notes. So up first here, we have this first formula here, which just says if you have the sum of a number times some function of k, something that depends on k, well, we could write that out as c times a1 plus c times a2 plus c all the way up to an. In other words, we could pull a c out of everything. C is a constant here. It doesn't depend on k. Kind of like the example from the last video where we had 12. And so we can pull that out and actually say, well, that constant can be pulled out. And we'd have c times the sum of the AKs. Okay, we refer to that as the constant factor. As a constant factor. We can factor out constants. And then the second one, I don't go into a lot of detail here. But the second one here says if you have two sequences here, AK and BK, and they're either being added or subtracted inside of a sum. Well, since a sum is just a big long addition problem, well, you could redistribute and actually have the sum of the AK sequence and the sum of the BK sequence. So this is our sum difference rule. Sum difference rule. We're allowed to distribute a sum across addition or subtraction. Doesn't work for multiplication. That idea does not work with multiplication or division, but it does work for addition and subtraction. And then underneath that here, we have these summation facts. And these are some rules that can actually be proven. We're not going to go into the details of proving them. But these can actually be proven by a process called mathematical induction. The first one just says if you add a constant up as k goes from 1 to n, then that would actually just be c plus itself n times. In other words, just c times n. So that one's actually pretty clear. We don't even need a proof for it. The next one says if we add up the first powers of k, so k would be 1, then 2, then 3, then 4. In other words, if we add up the first n numbers, n counting numbers, starting at 1, then that would be equal to n times n plus 1 over 2. The next one says we add up the squares of the integers, starting at 1. Then we have this formula. And the last one is talking about the cubes. We're going to stop it there, but there's actually formulas for adding up any series of powers, of whole number powers, 1, 2, 3, 4, 5, and so on. Okay. One important thing about these rules that I want you to note is all these sum formulas start at 1. So if you had a sum that started at 3, then you could still use this formula, but you'd have to realize I got to subtract off for k equals 1 and k equals 2, because my sum only goes up to, my sum starts at 3. Okay, so these sums all start at 1. So if we were to go back and go to 0, then that's going to change things as well. So, but we're mostly going to be dealing with sums that start at 1. That's not really an issue for us, but it could come up in a homework question with a sum they're asking you to work out. And so we want to use these properties now to compute some sums. What if we want to do the sums as k goes from 1 to 100 of k? In other words, we want to add the numbers from 1 to 100 up. This is actually related to a famous problem, a famous story in a way, about the mathematician Carl Friedrich Gauss. He was, when he was a kid in school, the teacher apparently gave the class these problems. This is back in the 1800s. So they didn't have calculators or slide rules or any of that kind of stuff. They had little chalkboards or slates to write on. And he said, all right, add up all the numbers from 1 to 100. The story famously goes that young Gauss figured out a really quick way to do it, and he came up with the right answer to his teacher very quickly without actually adding them up. And he probably used an approach similar to the formula that we're going to use. If you check out the notes, I actually give you a demonstration of what's purported to be the approach that he used. But here we just want to use our formula. Our formula is n times n plus 1 over 2. So we would say, well, n is 100. So 100 times, that should actually be, that should not be 100. Yeah, 100 times 101. Sorry for the typing mistake there. 100 plus 101, and then divide that by 2. And when you do that, you'll get an answer of 50-50. You'll get an answer of 50-50. First 100 numbers add up to 50-50. Okay, let's consider another one here. Let's go to the sum as k goes from 1 to 200 of k squared minus 2k. What I want to use here is my tools that I have are the sums for 1, k, k squared, and k cubed. So what I need to do is use my properties of sums to break it down so I'm dealing with those things. Then I can just use formulas. And so here I have a subtraction problem, and the 2 in front of the k to the first is just a constant which can be factored out. So I can rewrite this as sum as k goes from 1 to 200 of k squared minus 2 times the sum as k goes from 1 to, and that should be 200 of k. And then we can invoke our formulas for the sum of the k squareds and for the sum of the k's. Sum of the k squareds, our formula is n times n plus 1 times 2n plus 1 over 6. And for the sum of the k's, it's the same one we used up above, n times n plus 1 over 2. And then we just plug n, which in this case is 200, into both of those formulas. So we get 200 times 201 plus 401, all that divided by 6, minus 2 from out front, times 200 times 201, all divided by 2. And then we can add all that stuff up and get our answer, which I'm going to leave out here, but you could very easily multiply all this stuff out and get the answer, and it's pretty straightforward at this point. Okay, so that's just a little bit working with sums. In the next video, we're going to say, okay, well, that's great if we know the number, but what if we don't know the number? What if it's just some value? We'd still like to come up with a formula for the sums.